These are the Chapter 32 conceptual questions and problems. They were due on April 8th. They relate back to nuclear physics. So you're given this graph. It was a number of particles. You start off with 1 million, end up with 250,000 after 8 days. And the question was, what was the half-life? If I draw this out, I would go from 1 million to 500,000 to 250,000. Fantastic. That's in 8 days, so that would be 2 half-lives. So the half-life is 4 days. This was asking about if a half-life of something is 1 minute and something hadn't decayed by 15 minutes of a particular nucleus, what is its chance of decaying by from between 15 and 16? Well, if the half-life is 1 minute, it's still 50%. It's not like it ages out. It just is any 1 minute, there's a 50% chance of any individual nuclei decaying. Q11, U-235 has a much shorter half-life, so there's less of it around a day. It said that both U-235 and U-238 were created at about the same amounts in a supernova explosion about 6 billion years ago. So in the center of the Earth today, there's much less uranium-235. That's actually why it needs to be enriched when they get nuclear fuel for power plants. So this was the reaction when you were asked what X was. So if you look, the number of charges is 86 over on this side, so I need 86 on that side. So I've got 2 at the bottom, 222 on this side. I only have 218 up here, so I've got 4 up here. So this is the extra mass, and that's the extra charge. That is an alpha particle. For part B, I've got 55 here, 54 here, so I need -1, and then 0, so that is a beta minus decay. For C, 88 to 89, so once again, it is a beta minus decay. Electron -1 charge, 0 mass. For this one, we're given 29 to 28, so, and it's still the same total mass, so that's a beta positive decay. That's a positron. For Q232, or question 32, I was asked what this material is. So the choice was choice D, yttrium, because I have 1 mass, 0 charge over here, plus 92, 1 mass unit plus 235, that's a total of 236. Here I've got 53 and 0, so I need 39. Here I have 131 plus 3, because I've got 3 neutrons, each with a mass of 1, so that's 134. So I need another 102. So that is yttrium 102. For the problems, basically is asking here what the charge is. So it's 2 protons, 1 neutron, because all helium has 2 protons, all argon has 18 protons, all calcium has 20 protons, and all radium has 88 protons. So the total mass would allow you to figure out that. And I want to make sure I'm answering these correctly, so I'm going to pull out my book. Okay, so sorry about the delay. There we go. So yeah, for that problem 2 was basically asking how many protons and how many neutrons are in each one. So if it gives you the element name, you can figure out how many protons it is, because that's the atomic number. And the neutrons is just the mass minus the number of protons. Excuse me. For problem 17, it says the sun's energy comes from this equation, and it's asking you how much energy is released in the process. I don't know whether it wanted MeV or joules or things like that, but basically I take this as my reactant, this is the products, this is listed in the chapter, but it's also in, I believe, Appendix C. So I have this go to this, so there is a mass defect. So I have that amount of change of mass. That's the number of megaelectron volts per atomic mass unit. So I get 25.7 MeV is released. You could convert this to joules also. There's a couple ways you could do that. You could convert atomic mass units to kilograms, and then use E equals mc squared, or you can convert MeV to joules. Number 25, Let's identify the unknown isotope X in the following decays. So in this case, it was thorium-228. This one I screwed up because I looked at the next problem, which is actually problem 24, actually is the previous problem. So this is part B. So this would be 81 over here is the charge number. So that's thallium. For C, again, 4, -1. So that would equal 3. 7 and 0 would equal 7. So that's lithium. And then D, this is a gamma particle. So it's, again, nickel on the left side, just at a higher energy state. Last one, I estimated, so I don't think you're going to have to use the fancy formula in the book, but to drop to about 1% of initial value, I literally just went down half-life by half-life by half-life. Each half-life was 8 days, so 8, 8, 8, 8, 8, 8, 8. And then here, I'm between 1.53 and 0.76. You might split the difference, but it's going to be, you lose a greater part in the first part of the half-life. Because if you think about the curves, they're getting less and less steep. So even though this is closer, 1% is closer to 0.76 than 1.53, it would be kind of close to halfway in between 48 days and 56 days. So I ended up figuring this out. It actually was probably closer to 53 days. Sorry about me choking through this. Hopefully it helps. And hopefully you can go back and look at those problems and help you understand how to do a nuclear example.